Welcome. I want to welcome everybody to the 2024 Townsend Lecture. My name is Maury. I'm the president of the Montreal Center, and I'm going to spare you any talking on my part, so we can get out of here before tomorrow. So right now, like I said, I just want to welcome you to our talk. I want to introduce next our honorary president, David Levy, who's in Arizona, and he'll grace us with some words of wisdom.
Well, thank you so much. When I was invited to come and address you briefly at the start of the Townsend Lecture, I was filled with emotion because the Townsend Lecture is part of the heart and soul of our Montreal Center. It started in 1954 when G. Horley Townsend, one of the most active members of the society ever, passed away and left the Montreal Center a bequest of $25,000. In 1954, that was a very large amount of money. And the center decided to start a memorial lecture in his honor. And I can just tell you some of the people. Gerald Clemens, Carl Sagan was one of the Townsend lecturers. And if I remember correctly, one of the discoverers of Comet Shoemaker-Levy 9 was one of the Townsend lecturers. Anyway, that brings me to the poem that I would like to share with you. A couple of weeks ago, I went to Palomar Observatory for the first time in 30 years. And it was by far the most emotional visit that I've ever had at Palomar. Just standing next to the 200-inch dome. Boy, that's they knew how to bake observatory domes back then. It's kind of too bad they've forgotten now since then. But in any event, excuse me, in any event, the main purpose for my visit to Palomar that night was to see the partial lunar eclipse. And a lot of you might have said, oh, it's just 7%, you're not going to see anything. Boy, was that incorrect. In a way, it was as thrilling as the April 8th total solar eclipse. A very small portion of the top of the moon was covered by the Earth's central shadow. But the penumbra, the outer shadow, covered most of the moon at the time, and it darkened the moon significantly. It was wonderful. And so to celebrate that, and to celebrate tonight's Townsend Lecture, which I'm very much looking forward to, I'm going to quote for you Thomas Hardy's famous poem, At a Lunar Eclipse. When I first studied Hardy in Victorian poetry class, our professor told us that Hardy was actually a minor English poet. And we all looked at the professor as if he was nuts, and he said, yeah, I know. As a poet, he was minor. As a novelist, Tess of the D'Urbervilles, Far from the Madding Crowd, Hardy is one of the truly great figures in English literature. But I think as a poet, he ranks up there at the top as well. He saw a lunar eclipse from London, probably in 1902, and I believe he wrote the poem a year later. Thy shadow earth, from pole to central sea, now steals alone upon the moon's meek shine, in even monochrome and curving line of imperturbable serenity. How shall I link such sun-cast symmetry with the torn troubled form I know as thine? That profile, placid as a brow divine, with continents of moil and misery. And can immense mortality but throw so small a shade? And heaven's high human scheme be hemmed within the coasts yon arc implies. Is such the stellar gauge of earthly show, nation at war with nation, reigns that teem heroes and women fairer than the skies. Thank you very much. Back to you.
Thank you so much, Toby.
Thank you.
I can also let everybody know that David is going to be on the Global Star Parties again this coming Tuesday. They're resuming after a little bit of a hiatus, and you can catch him on the Global Star Parties, and he is fantastic with his literary references at the start, and also he contributes during a lot of the talks with giving a little bit of the historical context to what some people are sharing. And so I have a blast going on it with, and I know a lot of other people do. It's a great party. It's on Saturday nights on Explore Scientific. So I encourage everybody Tuesday nights on Explore Scientific. So I encourage everybody to join us on Tuesday night for the Global Star Party. Now tonight we're here.
One thing that I would like to add to that, the Global Star Party is quite different from a formal lecture like tonight, but it is a lot of fun. When I was at Palomar, the sense of history hit me in literal ways and a very specific way, because the history of Palomar and the history of Stellafane are so intricately interlocked. The reason they are is that Russell Porter, the founder of Stellafane, also designed the 200-inch telescope there. I wanted to share that with you.
Thank you. And for those that have never been to Stellafane, it's every Perseids weekend in the summer in Vermont. It's only a couple of hours drive from here. They've got an amateur telescope building competition. They have workshops. They have talks. They have a keynote at night. They have a teen workshop where teenagers from ages 13 to 17 get to do a project that mimics current research. So in the past, they've done a New Horizons probe. They've done a robotic lander. They've done what was the one that they did? They did a data processing of space telescope images. They've done a bunch of different teen workshops where it's hands-on, and that's available. It's a very cheap price, and if you camp, it's even cheaper. It's a great location because it's a dark sky, and on Friday nights and Saturday nights, everybody shares their telescope image. So in a dark sky, to be able to look through your 8-inch telescope, somebody 70 millimeter beside you, and then somebody else pulls out a 22-inch that they built at home. It's an incredible experience. I highly recommend it. So our talk tonight is our 2024 Townsend Lecture. Before we get to that, we want to talk to you a little bit about what our RASC Montreal Center is about. And our RASC Montreal Center always starts our public events with a land and sky acknowledgement. We not only acknowledge that we are on unceded Indigenous lands here in Montreal and at John Abbott campus, but we also share the sky with all of the First Nations and cultures and stories from across the world. And we can see that when we look at the lunar phases and how we refer to the moon at different times of the month. So right now we are at a waning crescent. We are almost at our new moon phase. And you heard David talk about seeing the lunar eclipse, and that partial lunar eclipse we saw just a few weeks ago. It means that right now the Earth, Moon, and Sun are in syzygy. They're fairly lined up, and the Earth-Moon orbit is now lined up currently with the Earth-Sun orbit. And so in just a couple of days, there will be a solar eclipse that's viewable from the South Pacific through Argentina and Chile. And that one's going to be an annular eclipse because the moon is going to be a little bit further from Earth than it normally is. So it's not going to completely cover the sun. So you can watch that feed on Insta, on Facebook, on Twitter, on TikTok. People will be posting their images. They'll be sharing their experience. It's hard sometimes to travel out to all of these locations to view the eclipses. We can see the stories of the eclipses in the First Nations. We can see the stories of the moons in the First Nations. And they always match what's happening in nature. So at the moment, we are completing the mate calling moon, when a lot of the moose are rutting their antlers to try to call the mates and ensure that they are ready for a winter of hibernation so that they can give birth in the spring and then raise their young so that they're ready to go for the following winter to survive the winter. That means that this next moon that's going to start in just a few days is going to be the animal fattening moon, where the animals will start to hoard food and prepare themselves by getting that fat reserve that they need for the winter time. On the settler side, we call this last one the harvest moon, because the moon close to the equinox is up just a little bit earlier in the night for a little bit longer, and is right along the ecliptic. So you actually have a very nice bright full moon that allows you to harvest food for a little bit longer. This next one is called the hunter's moon, because you use the full moon to go out on a hunt at night to try to get the protein that you can then store for the winter time. So we use astronomy for ourselves, for our passion, for our interest, but the First Nations and the Métis and the indigenous peoples across the world have been using it their whole lives to try to understand what's happening in nature.
I am here. Can you see me? We both live here. But do you really know who I am? Who we are? We are 11 different nations, 11 languages, expressing identity and territory. Each sharing our strength and our story. We carry seasons, gestures, and culture for today and for our future. We are 11 nations, 11 ways of living here.
Wendat.
Iyo, Kanyangahaga, Migma, Abeniki,
Waraslaway. Inu.
Adigma,
Eresnabe.
Naskapi. Inuit. Now you see us, and that's a start.
This is a beautiful video put together by our Quebec government just a little while ago, which helps us to understand a little bit about the diversity of these different First Nations tribes just here within Quebec. Through the RASC, our national branch, I've had the chance to work with Mi'kmaq, I've had the chance to work with Cree, I've had the chance to work with Innu, and I have currently coming up the chance to work with some of the, and it's hear some of their stories and to be able to share them during some of our public events and during some of our outreach. And within the RASC is the largest amateur astronomical organization here in Canada. We have centers across the country, 30 centers at the moment. Our Montreal center, the English one, is our only English amateur astronomy club in Quebec. The rest are all part of the French Federation. We have a dual mission. We both have the side where we try to encourage amateurs like ourselves to enjoy the night sky and share our pursuits. And we also try to provide outreach and public knowledge opportunities such as tonight's Townsend Lecture. We had an incredible one this past April, the total solar eclipse, which I know many of you got to enjoy with us here on John Abbott campus. Many of our members also had a chance to go out to the Eastern Townships where they got more than 3 minutes of totality. And over the coming year, we'll have an opportunity to revisit some of those images and some of those stories and even some of those videos as they're put together from our stories of the total solar eclipse. The other thing we do at the RASC is we have observing certificates. It gives people an opportunity to organize their journey into observing and to try to spot specific features or specific objects and learn how to understand the night sky by going through these small sets of challenges. When we go to our public events, it's hard sometimes to point out some of these specific targets because they're so faint and they're so hard to find. And we encourage people to star hop, but we know it's very difficult to do your first time around. So lately, what we've been trying to do is we've been trying to add different capacity to our group. We've currently reopened our Bellevue Observatory at the Morgan Arboretum. And we now have a group of astronomers in our club who are now certified to use green lasers safely to be able to point out objects in the night sky during some of our public events. So we'd like to acknowledge the wonderful effort put in by Robert, Brian, Richard, Santiago, Carl, Detlev, David, Lucas, and Alexi. And Saeed is on his way currently to being certified. All of these individuals can then determine exactly when we can safely view with the green laser and the spotters to ensure that any aircraft coming aren't bothered by our ability to try to point out things in the night sky. So this is just one of many initiatives that our RASC Montreal Center puts forward to try to improve our communication, but also what's available to our members and to the public here in Montreal. We have a lot of resources available to us. We have our 14-inch telescope at the Arboretum. We have a 16-inch telescope at our dark sky site down near the US border. We have the observing events and workshops, as I'll talk to you about in a few moments, clubhouses that we do. We have a library collection here at John Abbott that we run library nights from. And our current newsletter is actually now distributed nationwide through the RASC because our Sky News magazine that the RASC used to run is no longer operating. But we have some old copies of Sky News that we managed to pull out from the National Center. So if anybody tonight wants to take home any copies, it's a little bit less that I have to carry back up to the library. So I'm more than happy for you to take home as many copies as you want. These articles are written by professional astronomers as well as amateur astronomers. They're all edited and they're made in such a way that the beginner can approach it and get something out of it, as well as researchers and advanced astronomers can get something out of every issue. I talked a little bit about this idea that we do workshops and observing events. So we've been starting these Wednesday night events, astrophotography nights. We've had 2 of them so far, including this past Wednesday. Moon gazing nights, we've had 1 so far, and we have 1 coming up in just a couple of weeks. We have these wonderful library nights that we've been doing for many years now here at John Abbott. There's 2 of them coming up this term. And then we even have movie nights that we do for some of our members to just enjoy a nice old sci-fi movie that's space themed, to just get a chance to live a little bit in that sense of wonder that movies sometimes encompass for us. And then on our calendar, you'll see Saturday observing nights. Our members have access to all of this. Our John Abbott students through our partnership here at John Abbott have access to all of this. And anybody who's interested in becoming a member can email us and come to one of these as our guest. Get a feel for what RASC Montreal is all about. And we're welcome to share the night sky with us. Our public events that are coming up, we have one event that we do every year, which is just an incredible hit. It's called Spooky Nights. It's here at John Abbott College on the Friday before Halloween. Our John Abbott College Space Club, we have 3 of our exec here in the second row. They run a set of astronomy activities for kids that are space themed, but also Halloween themed. So it gives you a chance to enjoy Halloween and enjoy your love of space together at the same time. And we encourage our members, we encourage the public, we encourage families to come, bring your kids, and come in space-themed costumes. Enjoy being a bit of a space geek with us for a night, and get some candy to take home with you too, and a few cool crafts. We are also currently working with the Kingston Center to set up a Zoom with David Levy. David mentioned seeing the solar eclipse, and he mentioned seeing the lunar eclipse. What he didn't mention was that solar eclipse that he saw in the spring was his 101st eclipse that he's witnessed. This now makes 102 that he's seen. So he's going to talk to us a little bit about this history of observing eclipses. And as one of the comets that he co-discovered, Shoemaker-Levy 9, collided with Jupiter in 1994. We're at the 30-year anniversary of that collision. He's going to talk a little bit about looking back at what happened during that collision and what we learned from that process. We also have in December our Geminids meteor shower event. If you've ever enjoyed a night under the meteor showers, it's fantastic to watch. And most of the time we do that in the summertime, so we can sit back and chill and let the mosquitoes eat us alive. In the wintertime, you don't have to worry about the mosquitoes. It's really frigidly cold sometimes. But what happens is the cold air and the longer nights give you actually better viewing. So you get to see the stars of Orion. You can see the Orion Nebula with your naked eye. You can see the Andromeda Galaxy with your naked eye. Even at the Arboretum, where we're at the darkest skies in Montreal, but not really that dark, you can still see all of those features. And when you see a meteor in the wintertime, it just sizzles. It's incredible to see with your eye. So I highly encourage you to come out on December 14th for our Geminids meteor event. Now, David mentioned that our Townsend event was set up all the way back in the 1950s. Townsend gave us this incredible bequeath, and he gave us a little bit of the history, which is fantastic. So I'll spare you hearing that a second time. But I want to point out that while we originally started with, Shapley, who discovered the shape of the Milky Way and the size of the Milky Way galaxy, and Carl Sagan, and many others, including David Levy himself, giving our Townsend lectures. Since our centennial event, we've been focused on trying to bring to you some of the expertise we have in space sciences here in the Montreal area. So in 2018, we brought Steve Iris, who was the mission manager for the RADARSAT Constellation mission, which was run by the Canadian Space Agency in our South Shore and built right across the highway at MDA. We followed that up with the James Webb Space Telescope with Natalie Willette, who was the Canadian outreach scientist for the James Webb Space Telescope. We did, after that, during COVID, we had our Bishop's University exoplanet researcher, Jason Rowe, give us a talk online about the research that he's doing down there in Lennoxville. A couple of years ago, we had one of our former students and one of our former members, Emily Laflèche, who called in live from a moon simulation station in Poland to show us what it's like to be in an analog mission as an analog astronaut, to try to experience what it would be like to go and visit the moon as an astronaut, which is something that's quickly becoming a reality. And then last year, we had our McGill researcher, Andrew Higgins, who's here with us today, speak to us about interstellar propulsion. And he followed that up with mentoring one of our John Abbott students during the winter term. And this fall, he's taken on a few of our John Abbott students to help out as observers and hopefully participants in one of the projects that he's doing on the side with the high altitude balloon research. And several of our RASC members are hoping to be involved in that project as well. So our Townsend lecture tries to focus on what's happening here in Montreal and research opportunities that some of our students and some of our attendees might get a chance to hear more about and maybe even participate in down the road. So we're really excited tonight to have with us Jonathan Gagné from University of Montreal and from the Rio Tinto Alcan Planetarium. Now, some of you may actually recognize Jonathan because a couple of years ago in January, in our co-hosted stream with the physics department at the University of Guelph, we hosted Jonathan and two other researchers from the Institute of Research on Exoplanets, which is now the Trottier iREx Foundation, iREx Institute. And he gave us a our appetite. So we really wanted to get a chance to focus on the work that he's doing. And then this summer, he hosted one of our former students and one of our former members here from RASC Montreal, Willow Tager, as one of his researchers. So I got a chance to hear a little bit more about what he's doing, and I was sold on getting him in here to talk to us. I've had a chance to look at his CV, and there's one question that I'm itching to ask him, but I might wait till the question time afterwards. But he did his university and his PhD here at University of Montreal. So he is a Montrealer born and bred. He's really committed to space sciences and astronomy research here in Montreal. So without any further ado, I'll call on Dr. Gagné to give us our Townsend lecture.
Much for having me. So today I'm gonna tell you about some of the research that we do in my research group. So as Karen told you, I'm at the Montreal Planetarium and also at the Université de Montréal and the Institute for Research on Exoplanets, iREx. So today I'm gonna tell you about some of our most immediate neighbors in the galaxy. So I'm gonna be focusing on stuff outside of the solar system, but very close to us outside of the solar system. So I'm gonna talk a little bit about young stars, brown dwarfs, and planemos. So let's start if the panel works. Yes. So first, I'm gonna tell you a little bit more about brown dwarfs because not everybody knows about these objects. They are kind of not very well known yet. After that, I'm gonna tell you a bit more about our neighborhood of the galaxy and the young associations that we can find there, the young groups of stars that were born together. And then we're gonna get into planemos and exoplanets. So for example, what is a planemo? So I'm gonna tell you about that when we get there. So let's start with the concept of a brown dwarf. So you are all familiar with stars and planets. Brown dwarfs are kind of in between types of objects. They are sometimes called super Jupiters because they are much more massive than Jupiter. They're not that much larger, however, usually. They are also sometimes called failed stars because they are almost stars, but they don't have the nuclear fusion in their core to actually become stars. So there are these objects that are kind of in between stars and planets. So let's go back to how stars form. So here I'm showing you a computer simulation that shows what is happening in a molecular cloud as the gas falls into itself by gravitational collapse, and you start forming stars, these little white dots here. Those are stars that are appearing. So what happens when a cloud of gas like this falls into itself is that it falls in different small chunks that are each gonna become a star. And at some point, when the gas becomes has enough pressure and enough temperature in its core, some nuclear fusions ignite, and then you have a star that is born. And this nuclear fusion is gonna burn hydrogen, and it's gonna provide energy for the star to remain warm and bright for a very long amount of time for some stars and a very short amount of time for the most massive stars, but it's gonna provide them with energy. However, if you don't have enough gas that makes it into a small clump like this, it might not ignite nuclear reactions. And this is going to create an object that is very similar to Jupiter, very similar to a gas giant exoplanet with, you will eventually get clouds on the surface and you will obtain a brown dwarf. And these objects, there's a reason we haven't heard as much about them as stars, because they are harder to detect, they are a bit harder to study. Generally, you need infrared cameras to study these. So this is historically why we haven't studied these for such a long time, because we didn't have access to infrared cameras with a very high precision and a very high sensitivity before. So let's talk a little bit about the temperatures of stars. And this is actually something about the temperature of anything, even real life objects like hot iron. So when you heat something, at first you don't see any light coming from it because it's light in the far infrared. So if you have an object at room temperature and you turn off the lights, you won't see any light emitted by the object. But as you all know, if you have infrared glasses, you might see that people emit some infrared light because we are relatively warmer than the table, for example. And as you move to warmer and warmer temperatures, you start seeing light in the red, not just in the infrared. So some of the slightly warm parts of this iron there on the picture, you can see that it's actually emitting red light. And as you move to warmer and warmer temperatures, this color becomes orange, yellow, kind of white, and at some point it's going to become blue if you go to high temperatures enough. And that's why the stars that you see in the night sky that are blue are actually hotter than the stars that are red. And this is a bit counterintuitive because we like to say that warm colors are red, but it's kind of flipped here. So this is what is happening with brown dwarfs. They are so cold that we need infrared cameras to see them because they don't emit as much light and it's not light that is visible to our eyes. By the way, if you have questions, feel free to ask them at any point, but we're also going to have a round of questions at the end. So let's talk a bit more about brown dwarfs. So I mentioned they are faint and they are visible in infrared. So in order to detect them, the traditional trick is to take images taken with an infrared camera years apart, and then you compare those with images taken with a visible light camera, and you are looking for something that is only in the infrared images and that moves over time. So the reason you can see it only in the infrared images is, as I mentioned, because it's a very cold object. But the reason it's actually usually moving is that we can only find the nearest brown dwarfs to us because they are so faint. So the ones we are going to find just by their intrinsic motion in space, we're actually going to be able to see them moving. Because the closest something is, the fastest it will appear to move. So the brown dwarfs that we find are typically, they look like that. This is images taken by the WISE mission. And every jump in the image is a couple of months apart. So you have a full video that spans years. And then you can actually see this brown dwarf moving around. This is one of the nearest and brightest brown dwarfs. It's called SIMP 0136. It was discovered by our team in University of Montreal before I even started my PhD. So people like Etienne Artigot and Sandy Bouchard at the Université de Montréal who discovered this object. And we will come back to it at some point because it's a very interesting object. So as I mentioned before, brown dwarfs don't have nuclear fusion, but they emit light in space. So they actually lose energy over time. And because they lose energy, they become cooler and cooler and cooler over time. Stars, on the other hand, they have a relatively stable temperature for a majority of their life because the energy they lose by emitting light around, they gain back from nuclear fusion in their core, which does not happen for brown dwarfs. So the more massive brown dwarfs, when they form, so when the gas falls into itself, they gain some heat just because of the gas infalling into itself. This generates heat. And the more massive ones are going to gain more heat. So a massive brown dwarf is going to start hotter than a very light brown dwarf, but then both are going to cool down over time. And this means that if you only know the temperature of a brown dwarf, you are not sure what its mass is, because you don't know how long it has been cooling for. So this is one of the big challenges in brown dwarf science. With stars, in a lot of the cases, just knowing their temperature tells you a lot about the mass of the star. With brown dwarfs, this is not the case. So you really need to know its age, which is a key parameter here. Age is something about, so we're going to come back how we apply this for brown dwarfs. And for those who are, yes, you have a question?
Do you know the composition?
Oh, and in some cases, yes. I'm going to come back to this.
Okay.
This is, we do this with a method called spectroscopy, but we know the composition of some of the layers in the atmosphere of the brown dwarfs, and then we can deduce the compositions deeper by comparing with physical models. But in a lot of the cases, we know a good amount about their composition, yes. I have added also something, you might see the small kink at the start of the cooling track of the very massive brown dwarf. It doesn't cool as fast at first. This is actually something that is due to the burning of deuterium in their core. So brown dwarfs, even though they don't burn hydrogen, they burn an isotope of hydrogen called deuterium. This is more fragile, it's easier to burn, but there's so little of it that it's gonna provide them for energy for a couple million years, which is nothing in the lifespan of a star. So the sun lives for 4.5, it's gonna live for, 9 billion years in total. It's currently at 4.5 billion years. And the deuterium is going to be all burned out within 1 million or 2 million years for a brown dwarf. So it's nothing in terms of the energy it receives. It's just going to slow down the cooling at first, by a very small amount. And for the lightest brown dwarfs, it's barely noticeable, the impact of deuterium. So brown dwarfs are kind of strange when you talk about people to them, because then people are like, oh, are they in orbit around the star? And then every time I'm like, they can be, but they're also sometimes in orbit around the whole galaxy, like all stars. So they are sometimes freely floating around. So when you think about the other stars in our neighborhood, they are all in orbit around our galaxy, actually. They're not just moving around in random motion. They're on different orbits around the galaxy. So if you are looking at them from the Earth, they look like they're moving in every direction. And we will actually see some videos of that. But brown dwarfs can be the same. Sometimes they are just isolated and they're moving around. Sometimes they are a binary pair, like Lumen 16AB, which is actually the nearest brown dwarf. It's a brown dwarf binary. It's a pair of brown dwarfs orbiting each other. There are many binary stars, so it's kind of not too surprising to find binary brown dwarfs. Also, it tells us something about the formation of brown dwarfs. We have isolated brown dwarfs, like the one I showed you before, but we also have brown dwarfs that are companions to a star. And it's not an exoplanet because it's way too massive to have formed like an exoplanet. Exoplanets, for those who are not familiar with the term, it means planets outside of our solar system, so exo. But otherwise, it just means a planet around a different star. Planets usually form in the disk of a star, of a young star. So you have this disk of dust and gas that forms planets in there. And sometimes you can find objects like LHS 2397. It's not a very nice name, but it is the companion is way too massive to have formed like that. So it must be the case that it formed directly from the collapse of the molecular cloud. It formed like a star, but you just got two different masses, two different clumps of gas of very different masses, and they ended up orbiting each other, a bit like a binary star. So sometimes they are in orbit around the star. And there are cases where the brown dwarf is so light in terms of mass that we're actually not sure how it formed. And we find these gray scenarios sometimes that we don't really know how to classify. But some of them, like this one, we know it has to form like a binary star. So it's more appropriate to call this a brown dwarf than a star. It is also the IAU, the International Astronomical Union, has adopted a convention that is a bit easier to observe as professional astronomers, where if an object is more than 13 times the mass of Jupiter, we usually classify it as a brown dwarf. Smaller than 13 times the mass of Jupiter, we usually classify it as a giant exoplanet, like a gas giant. The reason for 13 is that this is the mass where the burning of deuterium is possible in the core. Even though it does almost nothing to the evolution of an object or what it looks like or what its atmosphere looks like, it's just a useful splitting of the definition. But it is becoming more and more clear that this definition is not the end of the story. There are many objects that we don't really know how to call right now that we will eventually need better definitions as we discover more of them. So the way we know about the temperature and the composition and the clouds of these objects is by a method named spectroscopy. So you take the light coming to you from the object and you split it across all of its colors. And you look at the intensity of every different color. And different atoms or molecules can have, they will absorb some very, very specific colors of the light. And you will see dark spots at very specific locations. And those serve as kinds of fingerprints for different molecules. And then this directly informs you of the chemical composition from the layers, the upper layers of the atmosphere where the light that you see actually comes from. But some of the deeper layers, the light gets all absorbed by the outer layers, so you don't see the composition for those layers, but those you need to infer with physics. So we can still directly know what some of the layers have in them in terms of chemistry. And we will come back to clouds by looking at the method of, the method of studying how light fluctuates over time at many different wavelengths. So you can take visible light or a very red light or infrared light or some infrared light at the longer wavelengths for a given brown dwarf, and you can see how it changes over time. So if you look at it for hours every night, and you look at the brightness over time, you will see shifts like the ones shown here in red and green and blue. At different colors of light, you will see different evolutions of the light. And this is due to different features at the surface of the object that are coming in view and going out of view as the object rotates over itself. And you can actually build models and infer from that what the types of features are on the surface of a brown dwarf and their temperatures. And even if you have enough data, their chemical composition and their different chemical compositions. So sometimes this allows us to see that brown dwarfs can have a cloudy layer that masks the deep layer in the atmosphere. But sometimes you have a hole in the cloud where you see a much warmer, much brighter region of the atmosphere, deeper, that has even a different chemical composition. And sometimes you can really see what is going on at different locations on the atmosphere. And this was done for Luhmann 16, I think this was Luhmann 16b, one of the two brown dwarfs that are part of this binary brown dwarf, which is the nearest brown dwarf. They have done this by trying many different 3D models of a surface brightness and comparing them with the actual variation in the light that they observed at many different wavelengths. And this allowed them to rebuild the surface feature, let's see it again, of this brown dwarf as it is rotating on its axis. So you can see that there are some bright spots and some dark spots on the surface. And this is likely due to a combination of clouds and maybe even some storms like at the surface of Jupiter. So you have many different features on the surface. So we're not able to see them directly, but we can infer what it must look like to reproduce the variation in the amount of light that we receive. And then something that really surprised me at the time they were discovered, 2 of the nearest 4 objects to the sun are brown dwarfs. And they were only discovered in the 2010s, so very, very recently. So one of them is Luhmann 16AB, which is also called Y1049-53 on the upper left of this figure. And this is a binary brown dwarf that we talked about before. And the next one is called Y0855-07. And this one is even less well known, but I think this is one of the coolest objects ever. It is actually literally one of the coolest objects in our neighborhood, in the sense that it's approaching 0 degrees Celsius on its atmosphere. And it is so cool that it is almost impossible to see it from the ground. Even with large telescopes in Chile, you can spend a whole night trying to get just an image of it, and it's almost impossible. So it was discovered by using data from the WISE NASA mission, which is an infrared spacecraft that has been scanning the sky from, I forget the start, but many years, and it ended very, very recently, something like 2010, 2023, 24. So it is the same researcher, actually, Kevin Luhmann, who found the WISE 1049. This is why it's called Luhmann 16. But I don't know why it was never called Luhmann something, Y0855, but it is one of his best discoveries, in my opinion. And it probably has a mass of 2 or 3 times the mass of Jupiter. And it probably looks a lot like Jupiter, possibly with different colors, with different types of clouds, but it would look like a planet if you looked at it. And it's one of the nearest objects to our sun. We have no idea how it formed. And it's just isolated in space, going around the galaxy. It's a very weird and mysterious object. So now let's talk about a mission called Gaia. You will see why it's very interesting to me. Gaia actually used visible light to measure precisely the distance of more than 1 billion stars in our galaxy. This is really a revolution to understand the 3D positions and even the velocity of stars. Here you can see a reconstruction of a camera zooming out of the solar system in the galaxy based on Gaia data. You can see like the Hyades flying by and the Pleiades on the upper right there, but you can see really their 3D structure. And this telescope did not see brown dwarfs, or almost none of them, because it uses visible light. However, it furthered our knowledge about the kinematics and the position of stars to an extent that it really affects brown dwarf science. And I'm going to come back to why that is. So it didn't only measure the positions of stars, it also measured the 3D velocities for a large number of stars. So now what I'm showing you is a fixed camera spatially, but we are moving 30,000 years per second in time. And we are looking at where the stars are going compared to the sun. So if we are sitting on the sun looking around, we see how the stars are moving. So it looks a bit random, like they are all moving in their different directions. But as you can see, stars are not fixed in space. If you wait long enough, you will see all stars moving. And this is the same for brown dwarfs. So that's why the very nearby ones, if you take images years apart, it's moving around. The same is true for the nearest stars. For example, Barnard's star, which is very close to us, if you take images of it years apart and you have enough zooming in, you can really see it moving around compared with the background stars. So Gaia, as I mentioned, doesn't see brown dwarfs, or almost none of them, because it works with visible light. So it would only detect the brown dwarfs that are the hottest and the nearest to us. So there's really just a handful of brown dwarfs for which we have a very good distance measurement from Gaia. So let's go back to the formation of stars in molecular clouds. This is a more recent simulation of star formation. It's really nice. It's created by the Starforge collaboration, and they put a lot of effort to making it really look nice as well as physically robust. And what you can see here is that some young stars are forming. They are ejecting some of the gas back into the molecular cloud, and they modeled all of these physics. This is actually a model, not just a visualization. And the massive stars with their light, it's moving the gas away, compressing the gas, forming new stars, and clearing the gas from the star forming region. But what I want to focus on here is we are forming many stars in one such event like that. It's not just one star that is forming. And at first, this is creating a couple of associations of stars. So this is groups of stars that are born together and that are moving together around the Milky Way. And they're gonna keep moving together for a long amount of time as they age. And that allows us to understand that they are part of the same group because they're moving together. So here I'm showing you a small visualization of, imagine a molecular cloud going around the galaxy, and then it's going to form stars. At first, they still move together, but then as it rotates around and the different stars encounter different gravitational pulls from other clouds, from massive stars, they're going to get mixed up around the galaxy. And at some point, you're not going to be able to tell that those were born together. They're going to be mixed in with all of the older stars. And really, you can't go back in time with enough precision to know where they were born. But if you catch them young enough, then you are going to be able to tell that they moved together. In some cases, when you have enough of them, you get something that's called an open cluster. So these stars remain gravitationally born because you have many, many of them that are densely packed together. And these open clusters can survive for a lot longer. They will still get gradually mixed away. Their members will be torn apart very slowly. But the open clusters can survive for a very long time. This is a view based on Gaia data of all of the nearest open clusters around us with their motion of rotation around the galaxy over time, as measured by the Gaia spacecraft. And the associations of stars that are not dense enough, that are more loose, those will survive for maybe 500 million years. It's not very long. The open clusters will survive for billions and billions of years as cohesively moving together groups of stars. So, for example, one of the discoveries of Gaia is a massive structure around the Hyades, which I'm highlighting in red in this video. This is called a tidal tail. And this is what I was referring to when I said that the open clusters get gradually shred apart by the galaxy, but it takes a long time. The Hyades is about 600 million years. It's completed about 3 full revolutions around the Milky Way. And it is in the process of being shredded by the tidal forces of the arms of the Milky Way that are pulling apart on it. But it's taking a long time because there are many stars in there which are gravitationally bound, but it's creating this elongated structure of stars that the Hyades are actually losing. And something that's remarkable about this structure is that, let's come back to the start of the animation. The yellow line points from the Hyades to the sun. So you can get a sense of scale. The Hyades is the nearest open cluster, but look how large this structure is. It's about 800 parsecs in length. So in light years, that would be a few thousand light years in length. It's a huge structure, but it's not very dense. There aren't many stars per unit volume in there. And if I was to show you all of the stars in that same volume and highlight them, there are so many that it's very hard to pick apart that there is this structure there around the Hyades. We found the Hyades, the core of the Hyades, historically because it's very dense, so it's obvious that there are more stars there. But if you go in the tidal tails, it's not obvious that there are stars that belong to the Hyades. The only way you can tell is that they all move together in space. And that's what Gaia allows us to do. We are rediscovering the neighborhood and many of its extended structures around all of these associations using Gaia. So we are literally finding new populations of stars that we didn't know belonged to some groups that were long known. And we are also finding new associations altogether. This is an example of recent discoveries around, I think that was 10 nearby open clusters, and they all have elongated structures around them that are co-moving with them. It's not in all cases that these are caused by tidal forces. Some of them are just looser populations of stars that were formed in the same molecular cloud, and they are almost born at the same moment, but they are more loose. Like you saw in the simulation before, you form some dense regions and some other loose regions of stars around them, but they are all related to the clusters that they are around. They are all about the same age. And in our own group, we have also discovered a new association of stars that is tiny. It's just this small group of stars there that you can see moves together against the background of stars. And the reason we had never found it before is that there's just a small bunch of stars in there. It's a very small star forming event. However, the red dot there is Luhmann 16 AB. That's the nearest brown dwarf, the binary brown dwarf I was telling you about. It had been long suspected that Luhmann 16 was slightly young, about 600 million years, based on a study of its atmosphere. And our group found this other bunch of stars that were moving at the same time. And all the other stars with different techniques of age dating, they also look like they are 600 million years old. So it's really a cohesive picture of probably where those are siblings to Luhmann 16, basically. And it was never discovered because the stars are not obviously young. They're not super, super young. They are old enough that they don't have very odd features that you would recognize in young stars. And they are not dense enough to be obvious that they are moving together unless you have this massive data set of position and velocity for all stars. And even with the massive Gaia data set, it's not obvious that this structure exists in there. We had to use machine learning techniques to actually figure out that these stars are moving together. And that was the work of my now PhD student, Leslie Moranta, who did the bulk of this work of applying machine learning techniques to discover new groups of stars moving together. This is another part of the work that she did. So here I'm showing a lot of open clusters and loose associations of stars discovered in Gaia by a different group called Kunkel and Covey. And my student, I asked Leslie to focus on the neighborhood because all of these other studies, they missed stars in the neighborhood because of the way they did the calculations. And Leslie literally filled that gap by finding all of the loose associations near us immediately in our neighborhood. And that's how we found Oceanus, the other moving group with Luhmann 16 in it. So just quickly, the reason why you might miss objects that are too close to you is that imagine you have a flock of birds that are passing by you, and you are just looking at the angle of their motion. They would seem to all be moving with different velocities. You really need to have the full 3D velocity of them and compute it from a distance to see that they are all moving in the same direction. So the other studies were only using projections of the velocities so that they could only discover the distant ones that all seem to be moving together because they are far apart enough. So now let's go to the next slide. So one of the questions someone might ask is, what is the link with brown dwarfs and why is it interesting to discover young stars? There are two main aspects of this. First, young stars have many different applications that are super useful, but even those that are not so young, being able to know their age with precision is extremely important. So when you have a group of, let's say 500 stars, you know they all have the same age. You can determine what that age is with a really high precision, because you can use different techniques to measure the age of stars on different stars and then stack all of these measurements together and get a very precise measurement. If you have just one star that is isolated in space, depending on its temperature, sometimes you have just no method to estimate its age. Sometimes you have a method to get a rough estimate, but it's not very precise. Sometimes you have a relatively precise estimate if you're lucky enough that it's a very specific type of star. But if you have 500, in those 500, you have some of the stars that you can really date more precisely, and some that you can date with less precision, but you can combine all the measurements. And when you can do this, any exoplanet around these stars, suddenly you know their ages too, because they form very rapidly around the star. And you know for how long their atmospheres has received UV light from the star. And you can start wondering about, oh, how long has this rocky exoplanet degassed from the rock in its core? And you have many, many questions that you can start answering. Which in most cases, usually when we look at an exoplanet or a star, we don't know its age. We really don't even have an estimate of it. So it's very interesting for that. And when you catch the very, very youngest stars, it's very interesting too, because you can find stars with disks around them that are still forming exoplanets. And you can actually catch exoplanets in formation. So imagine you have 100 stars with all different ages through the steps of exoplanet formation. If you can image that disk and study it for all of these stars, then you get a snapshot in time at many different planet forming epochs. So this is really useful to understand the steps through which exoplanets form. There's a lot of unknowns in there. And even for our own solar systems, there are still unknowns about how all the planets form. Did we form more planets? Were some of them ejected? There are a lot of open questions. And when you find young stars, it's also one of the only ways when we can directly image a planet, the light from the planet around the star. This is possible when you have a gas giant exoplanet around the star. They work a lot like brown dwarfs. When they form, they are hot and then they cool down over time. And it is when they are hot that we can actually see their light directly. So if you catch a gas giant exoplanet at a very young age, it is possible to get an image of it, like the one I'm showing on the upper left here. Oops. So currently, we have found more than 5,700 exoplanets, found and confirmed, because there are more candidates, and their properties are all over the place. There are all kinds of sizes, temperatures, compositions around all kinds of stars, and only a tiny, tiny minority of those we know the ages for. So there might be something like 50 exoplanets right now for which we have a really good age for them. So it's really, we are at the start of adding this new parameter in all of the exoplanets in terms of age. And one thing that is very hard to do with exoplanets is to measure their light directly, like I talked about and like I am showing here. This is actually HR 8799. This is an exoplanet system. It is the first system of exoplanets that was ever imaged around the star. So system as in there's more than one planet. And this was done at Université de Montréal right before I started doing research after my BSc in physics. René Doyon, who then became my PhD advisor, was in the process of receiving these data sets, and he was very excited about this. And what you're seeing in this video So just this image, something like this was the huge discovery when just before I started. But then they kept taking images over time, and you can actually see the orbits of the exoplanets around the star. This is a very unique case of a star that is very young and has giant exoplanets far enough from the star that you can image them. And we now know that this is a really odd system. We used to think, oh, maybe there are many more like this one, but there aren't. It's a very rare type of star that for which we can image the planets like that. However, even in this case, you can see all kinds of weird shapes in the middle there that are changing over time. Those are defects in the mirrors and the lenses of the telescope and the instrument. And we have algorithms to try and remove the light of the star. But as the camera moves around, as the telescope moves around, the camera deforms a little bit and the optical defects move around. And there are aspects of the light from the star that is affected by that. The shape of the central star changes a bit. And it becomes impossible for us to remove everything about the light of the star. So you get these weird shapes, and you can see that the inner fourth planet is a bit its light is a bit deformed by these effects. But in reality, all of them are a little bit. And this means it makes it very hard to study the light from these exoplanets because we need really aggressive instruments and data processing techniques to remove the light of the star. And it gets even worse for the other exoplanets, which we do not see directly. We only see the eclipse with the star, or we only see the wobble of the star. It's very, very hard to directly study the light of the star. But when we get a brown dwarf that has characteristics similar to an exoplanet, the same type of temperature, clouds, we can get such good data on them that is incomparable with what we can do for exoplanets because we are not bothered by the star. It's alone, so we can get orders of magnitude better data on them. The problem is finding them first. Once we have them, studying them is much easier. But then let's go back to this plot I talked about earlier. Imagine we have a brown dwarf that we find, and then we split the light in all its color. We determine it has this temperature. We don't know its mass at all. So what our group started doing is combining the field of study of brown dwarfs and young associations to actually find brown dwarfs like Lumen 16 earlier that is part of a group. And suddenly you know the age, you know the temperature, you know the age, and now you can pinpoint what the mass is by comparing with physics models of how brown dwarfs cool over time. So now you get a prediction of the mass. And we started finding objects that didn't fit the definition of a brown dwarf. They were 8 times the mass of Jupiter, 9 times, 10 times, smaller than the IAU definition of a brown dwarf, and the same mass as some exoplanets in the system around the star. But then we didn't know how to call them. So we started to call them planetary mass objects, and that got contracted into planemos. And those are sometimes also called rogue planets because they're not around the star. But we tend to avoid this term in the scientific literature because this suggests that it formed like a planet and then got ejected. But we don't know in reality how they formed these objects. They might have formed like stars. And we have even seen a case of a planemo that is a binary. And this is a sign that it must have formed like a star because you don't get binary planets orbiting around the star. And it would be even harder to eject a binary planet without splitting the binary apart. So it is very likely that they can form like stars, but sometimes they might also form around a binary star as a giant planet around a binary star. And the interaction of a binary star can very easily eject giant planets. So you can we really don't know how they got there. So it's really a contraction of planetary mass object, which is the most the way to call them that will shock no one in the community, because yes, they have a planetary mass and they are objects, so we don't know what they are. So we contracted this into planemo. But they have very similar properties to exoplanets. And now what my team is doing, we are building a giant database of all of the young stars in our neighborhood and all of the brown dwarfs to really merge these two together and find new planemos that we didn't know about. So currently there are only a handful of known and confirmed planemos. There's something like 15, depending on how you count being confirmed or not. But there are hundreds of thousands, if not millions, of young stars with known ages, from which we need to find new associations of stars in there. And we have thousands and thousands of brown dwarfs for which we know parts of their velocity, but not all of it. And we can start asking, are they moving in the same way as this particular association? So analyzing all of this data becomes really, really hard. So that's why we put together a database, and we called it the Montreal Open Clusters and Associations Database, MOCA, when you put it short. And the reason we did this was that there is so much data in Gaia. There are so many papers coming out with so many new associations. You can get a month where 2 different papers appear in the literature, and they each discover 5,000 new clusters or associations, but half of them are in common and they give them different names, and they found not exactly the same stars in each. So it's a mess to study this correctly. And we were starting to spend a lot of our times combining spreadsheets and just to get started. So we decided to move everything in a big database to really help us with this process. And now with the database, we can now pull a list of all the known exoplanets, for example, and just pinpoint in color those for which the ages are known. And here we can compare the period of the planet around its star as a function of its radius. And we can look at the distribution for those that are young versus not young and start to see, are there differences in their populations for these objects? There's one long-standing problem in exoplanets where there's kind of a gap in the radius distribution of exoplanets. It's like there are some types of radius of exoplanets that don't seem to exist, and we don't know why. But when you look at younger ages, this gap seems to be filling. So the reason might be that those are planets which atmosphere gets eroded over time by the star. This is one of the current hypotheses of why this is happening. So this is the kind of questions that we can answer by finding many more exoplanets with known ages. We can see how their population characteristics evolves over time. And then we can start to understand what happens to these exoplanets. We also have in our group a program that searches for exoplanets specifically around the newly young stars that we discover using the method of radial velocity, which means you look at a star and you are looking for its wobble in velocity along the line of sight, and you can see an exoplanet indirectly this way. And my PhD student actually recently found a very interesting candidate there. And already our first discovery might benefit from having an age for it, because it's something that is called a hot Jupiter, meaning that it is a very large, very massive planet, very close to its star. And these types of exoplanets are a bit mysterious because we started finding these in the exoplanet community because they are much easier to find, because they're so close to their star that they're pulling really hard on the star, and they are very massive. So they are doubly pulling very hard on the star. But no one expected to find these because we didn't know they existed. We didn't know they could form there because all of our theory of planet formation did not allow for this. So when astronomers started finding them, those were the first types of exoplanets ever found. And when they started finding those, everyone was like, what is going on? Those should not even exist. And so there are multiple competing hypotheses of how these form. And we think that most likely they have to form far from the star in the disk because there is not enough gas close to the star to form a really massive planet. They have to form far, and then they have to migrate inwards to the planet. So some process is modifying their orbit, so they're spiraling inward and then they're staying there. But this one that we just found, it is so young that it must have migrated really fast. And it's surprising how fast it must have migrated to exist for such a young age. So already we are finding some interesting puzzle pieces by finding exoplanets directly around young stars, and more specifically, not just the young ones, but stars for which we know the age precisely. So when I showed you the figure previously, you can see how few colored points we have here. Those are the exoplanets with known ages. So we decided, let's start with a sample of stars that we know the age for, and let's search for exoplanets around them. And we have a good way of doing that because we have this database of all the young stars. And the database is also what I use to make all of these animations in there with a software called Gaia Sky. It's made specifically to visualize Gaia from the data from the Gaia mission. But we have built a interface between that and the database so we can pick any young association of stars and just overplot it on top of the other ones with colors and see their velocities. And I actually use that for science very often. Like when I see discussions of two different groups, I'm like, oh, which were these groups again? Are they far or close to each other? I can just open this up and see in 3D where they are and how they are moving. And it's actually very useful for research. Sometimes you just notice, oh, these two groups that people are talking about, they actually touch and they are one larger structure, and you would not have noticed if you didn't really look at them in 3D. So that is it. So thank you for your attention. Don't hesitate.
So before we take questions from the audience, I just want to, I know David wants to give a comment and then we'll take questions from the audience. David?
I just wanted to say that this was fabulous.
We can't hear you.
You're muted.
I'm sorry. Can you hear me now?
No, we still can't hear you. Can you unmute or mute and then unmute again?
Is he muted on our side?
No.
How about now?
Hold on. I know
Yeah,
what's
you
going
must
on.
be sharing the other
I know what's
computer,
going
right?
on. Give me a moment. It's okay. Go ahead, David.
Can you hear me now?
We can.
Yes.
Great. All I wanted to say, and I'm sorry I had to wait so long for this comment, is that I thought your Townsend lecture tonight was fabulous, with a capital F and a capital S, as my grandfather would have said. And congratulations, you gave a lecture that really brought into focus, pardon the pun, this burgeoning field of exoplanets. And I think it gave me a new insight as to what this field is going to bring into the future, and you will be a big part of it. Congratulations. Thank you.
Thank you.
Thank you, David.
Thanks.
Okay, from the audience.
Yes.
These associations, they're moving from where and to and why?
Okay, so they are on orbits around the galaxy like us, but they are on slightly different orbits around the galaxy. So where they're moving is in not circles, but they're moving around the galaxy. But seen from us, from the sun, we are also moving, but they're moving in a different orbit. So from our point of view, they're just moving in some direction, some random direction. But if you waited for long enough, we would start curving on the orbit and they would start curving too, and we would see all these weird patterns. But we are looking on the scale of dozens of years, and their orbits are 250 million years around the galaxy. So they just look like straight lines when you look at their motion on our human scale. But they just look like just bugs flying around in linear motion but random direction. That's what it would look like.
Could they be moving towards some gravitational
Well,
source?
the gravitational source is the whole of the Milky Way, and they're moving around it. So it's not perfectly ellipses like an exoplanet, because it's not a point source of attraction, it's diffuse. So if you trace their orbits, it looks like a spirograph. I don't know if you've ever played that thing. Like it doesn't really close, and you get all these flowery patterns. So the orbits of stars around the Milky Way look a bit like that. So this is what their motion would look like if you look on this hundreds of millions of years scale.
The Gaia mission, what exactly is that?
Okay, so it's a spacecraft that was launched at L2, it's called, it's a Lagrange point, L2. So basically you have the Earth going around the sun, and L2 is kind of behind the Earth, but at a point that is a bit stable because it's the force, the centrifugal force it's experiencing is balanced with the Earth and the sun pulling the other way. So you need to spend less carburant, how do you say that?
Fuel.
Less fuel, thanks. You spend less fuel to stay there. And you can look at the stars without being annoyed by the sun for a long amount of time. So it's a very strategic place to place astronomical spacecrafts. And there are many there, including James Webb. But Gaia is there and has been there for a long time. And it's actually measuring the positions of all stars. It's taking images, but then it cannot send us all the whole images back to Earth because there are too many images and they're too large, and the internet connection to Gaia is not fast enough. So what it does is that it detects the positions of all stars, and then at the other image it takes, it matches the positions of all stars, and then it figures out, oh, which stars move with respect to the very distant quasars. So what is moving and what is not moving. And by doing that, you get something called the parallax. Like if I move my head like this, I see the front row people moving more than the back row people. And the stars do the same thing as the Earth and Gaia rotate around the sun. So you can actually see the wobble of stars. And that is due to their distance. So by doing that, you know their distance. And then you also see the motion of the stars over the years. So it's measuring the position and the motion of the stars. So it's a spacecraft with a camera, with many different instruments on board. Yes?
I think it's supposed to run out next year.
That's possible, but have they not extended it further? Because the data releases that were supposed to come out were delayed because of COVID. So I don't know what happens when the fuel. No, the scientists were getting COVID. But it's possible that the fuel is ending soon. But this is often the case with these missions where they extend them beyond their initial projected lifetime. And I would be shocked if they don't prolongate Gaia because it's been so. It has produced so many papers.
Is there any plans for a Gaia 2?
There are some plans for a Gaia 2 that would be infrared, which makes me very excited because you could get brown dwarfs, but it's at the very, very early stages.
Thank you.
Yeah. Yes?
How do you get the component of velocity in the radial direction?
Excellent question. Using what is called the Doppler effect. So when you split the light of the star, you get this whole pattern of light intensity, and as the star moves towards you, it's all shifted to the red, to the blue, and if it moves away, it's shifted to the red. It's a bit like sound, and a source approaching from you is going to sound a higher pitch. So the light does this too, but it's much more subtle because light travels very fast. But when you get a high resolution spectrograph and you can actually compare either two objects with each other, you can get a relative velocity between the two. But the easier way is when you know the wavelengths of all the dark lines of the molecules, then you can shift them with respect to our like rest velocity. So then you can really get the velocity of the object.
So that's done by separate observations. That's not done on board Gaia.
It's actually done on board Gaia. This is a really nice feature of Gaia is that they thought about the whole 6-dimension thing, like the 3D position and the 3D velocity. They realized they were measuring the lateral velocity just by many images. They were measuring the parallax, and all that they needed to complete the 6D picture was radial velocity. So they added a small spectrograph that is focused on one specific very narrow region of the light to just get the radial velocity, but not for all the billion stars, just for the brightest ones. So it has something like 30 million radial velocities, which is already a huge data set that eclipses everything we had about radial velocities. So we have only about 30 million stars for which we also have a radial velocity, so a 60 position. And this is how we were able to find groups so close to us. We needed that component of radial velocity because the other studies, they were using the larger sample of stars without the radial velocity, so they only had the projected velocities, hence the problems with projection effects.
Is it specifically using one of the hydrogen wavelengths?
It's using the calcium triplet. Yeah, I forget the exact wavelength, but it's in red optical.
So does that
Calcium
limit it
triplets.
to only specific types
Yes.
of brown dwarfs?
No, stars.
Or only brown dwarfs then?
No, only stars.
Only stars.
Gaia is only measuring the motions of stars,
Yeah.
but it's limited to some range of temperatures of
Okay.
stars. It cannot do any type of star because you need that calcium triplet.
Yeah.
But it shows it because many stars have it due to stellar activity, and it's also useful to understand the activity of the stars. So they do separate measurements on this calcium triplet. And it's a deep feature that is easy to detect, and you have many, a lot of information about the velocity because you have a lot of small lines in there. So it's easier to like align them together when you have many patterns to match. Yes?
I was very intrigued by the concept of deuterium burning.
Yes.
Deuterium is a stable isotope, so I don't assume it's decay. But is it oxidation, like burning that we understand?
Oh, it's nuclear fusion. It's just, it just doesn't require as much temperature to fuse deuterium.
So fusing two deuterium
Yes.
into helium-4 or?
I forget what you get, but it doesn't require as much energy to do it. It's just much easier to fuse it, but it's rare. That's the issue. There's not a lot of it.
So basically, the heat generated during that phase
Yeah.
of the initial phase is nuclear fusion heat,
Yes, from deuterium.
but doesn't reach the stage of emitting visible light to the surface.
Okay, so nuclear fusion never directly gives you visible light at the surface. It heats the core, and then the whole thing emits light at the surface because the core is heated. What happens with hydrogen is that it keeps burning hydrogen for a very long period of time. So you add energy all the time to your star because it's always burning hydrogen. Deuterium, it does that for a million years or two. And so the brown dwarf is gaining energy at first, and it's replenishing the energy it's losing. But then it's so short-lived that there's just no more deuterium after a million years.
Heat at the core to reach the stage of sending photons to the surface.
It does send photons to the surface, but it never reaches the stage where it becomes a star.
Right.
Because there's a much higher threshold in temperature to start burning the hydrogen. And if you never reach it, then the hydrogen is just gonna stay there. So even the burning of deuterium doesn't make the brown dwarf brighter. It's barely making up for the lost energy due to the light leaving the brown dwarf. Yeah, so it's kind of compensating, so it's not cooling as much, but then deuterium is depleted and then it starts cooling very fast. Whereas the star might start cooling, and then the core condition is reached where burning starts, and then it like brightens, and then it stays stable for a very long time.
Another quick question.
Yeah.
The open clusters that you talked about, the one that houses the WISE 1045.
Yes, Oceanus.
Yeah, what's the radial or angular resolution there? So how wide is it?
Yeah, how wide in terms of minutes of arc viewed from Earth?
Yeah.
I don't remember, but it's going to be pretty large because it's very near and it's very diffuse. So it's going to be in the degrees. Okay. So I would have to look it up, but it's huge on the sky. But it's hard to, you couldn't like even point at your telescope because it's like one star there,
Yeah.
one star there, and then one star there. It's very diffuse. What's the question here? Here.
So this might seem a touch unrelated, but I wanted to ask, so stars are moving around, orbiting around each other a bit. Would we say the same for galaxies? And if so, are we studying that as well?
Yeah, the galaxies are also moving with respect to each other. But when I do my own research, everything I'm studying is sitting in the same galaxy. So let's imagine that I take hundreds of balls and go on a plane and throw them around and study their motion. And then the plane is moving, but then you have another plane with other balls moving in a different direction. For my science, I don't need to account for the motion of my own plane to study the balls and how they move with respect to each other. So it's kind of the same scenario where the other galaxies, they're moving in completely different directions and their stars are also orbiting the galaxy, but I don't need to know the speed of my galaxy with the respect to the other one to actually do the research in my neighborhood of the sun. However, if I were to study stars in the other galaxy, then I need not only to account for their orbit around the galaxy, but I need to also know the motion of the galaxy itself. So this becomes important when you study things at the larger scale specifically. So when you are at the local scale, you don't need to know the velocity of your own galaxy because everything you're studying has this velocity. This comes up in all the fields of astronomy, like the relative motion of us around the sun, the Earth around the sun, but then the sun is moving around the galaxy, then the galaxy is moving around, it's moving like with a large cluster of galaxies, and that cluster is moving in some direction. There's like so many layers of velocities that you can end up asking yourself, what is the real total velocity that I have? And that's a very hard question. It's a very hard question to answer because there are so many layers like that of things moving with respect to each other. Yeah. Yes?
You mentioned brown dwarfs teeter at the edge of fusion and non-fusion. And we are trying to replicate fusion on Earth now.
Yeah.
In your opinion, do you think we might find something interesting that can help us get there?
So do you mean will in astronomy will we understand something about fusion that would help nuclear reactors here on Earth?
Especially with brown dwarfs.
That could happen. It would be hard because it's such a short time where fusion happens, and it's so few brown dwarfs that are young enough, and they are so faint that detecting stuff like neutrinos would be very hard. And that's usually what you would do to like understand the fusion at the core. It's not that it's impossible, but I suspect that the technology of the nuclear fusion reactors we build here might progress faster than the technology of detectors specifically for brown dwarfs. But in the case of stars, it's already been the case that our understanding of fusion, there's a lot that comes from our observation of the sun with solar neutrinos and stuff like that. But for brown dwarfs, it's so hard to know and constrain exactly what's going on in their core. A lot of what we say happens in terms of fusion of deuterium at their core is actually based on physics, on the models of the interior of the brown dwarfs, not that we observe directly what is burned. We can see that the cooling curves of brown dwarfs are slow at first and then faster, but we don't see that with a really big enough precision to really help understand nuclear fusion at that scale. Yes?
We have a lot of amateur astronomers in the audience. I'm wondering, now that we know that brown dwarfs are out there, we didn't know that before, and we have a lot of new rapidly changing technologies, especially in camera detectors that go beyond the infrared, like 1,000 nanometers and beyond. Are brown dwarfs observable with amateur equipment?
That's a very good question. You could take, I would say, look for Lumen 16. This is clearly the brightest one. Well, Lumen 16 you can do probably with visible light. So you can, this is an odd example that you can probably see with a good camera, not even in the infrared. But have a look at its magnitude on a service like Simbad, just type in Newman 16, and it might be doable. Otherwise, there are good cases like Simpo 136, the one that I showed before. That's going to be challenging with amateur equipment, but we might be getting there. I haven't checked, but it's worth having a look, because if you have some of the latest infrared cameras, maybe you would be able to. I'm not sure. Yeah. Yes.
There's one more.
Yeah.
So a brown dwarf is the size of Jupiter,
About
but
that.
it's 10 times the mass, and 30 times the mass, and it's warmer
Yeah.
than Jupiter. So how does that square with the equation of state? Like,
Quantum
we know
physics.
both-
It's held up by the pressure of degenerate electrons, like white dwarfs and like black holes. Well, not black holes is not degenerate electrons, but it's quantum physics too, and it has this property of where you add mass and it's not growing as fast as you would imagine it would grow, and sometimes it's like the case of black holes, it even shrinks, and that happens with brown dwarfs too. If you add mass, it gets larger, larger, larger. You add more, it gets smaller, 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 and then you add more, and then you get a star, and the size explodes. But it's all about 1 time the radius of Jupiter. This is because, so it's held up by electrons not wanting to sit on top of each other. And as you add mass, it gets warmer, and the electrons get, it's kind of a stretch to say this, but physically smaller. So their wave function gets smaller when they are warmer, so then they can pack more efficiently. And that it's really the electrons that are stopping the collapse of the brown dwarf. Because when I said that the molecular cloud collapses into itself and forms a star, if you didn't have anything happen, it would just collapse by gravity forever, and it would just fall into this small, small point. But what happens is that nuclear fusions ignite, it gets warm and it expands. The warm gas wants to expand, so it kind of counterbalances the gravitational pull, and that's what stops the star from collapsing. But brown dwarfs don't do this. So even with deuterium burning, it's negligible in terms of the pressure that it adds. So it's not really stopping the collapse. So what stops the collapse is the same as Jupiter, and it's the same as white dwarfs. So when a star dies, when a star about the size of the sun dies, there's no longer enough hydrogen in the core, so it keeps collapsing. And what is the next thing that stops it? It's electrons kind of hitting each other and not wanting to sit on top of each other. And for this type of object, when it's really electrons that stop the fall, when you heat it up, it gets smaller.
Okay, so I've got a question, but it has nothing to do with your astronomy and astrophysics.
Okay.
I tell my students sometimes that, physicists have like this unique way of looking at the world. And Dr. Gagné is a physicist by training, and he wrote a book about the physics of coffee filters. And I'm wondering if you want to share with us just a small bit of your findings about coffee, because I know we're all coffee aficionados.
Yeah. I fell into this rabbit hole. Like I started by just bringing my own coffee gear at the telescope because I didn't like the coffee they had there, and so I started traveling with my hand grinder, before it was like this hipster thing, because it started when I went to like Hawaii and Chile, because they had like a can of Folgers that stayed open, and I was like, so yeah, I traveled with my own coffee, and then when I was doing postdocs, I was moving in different cities, and my coffee completely changed, and I was like super confused. So I fell into this rabbit hole of understanding what is going on, and like how the minerals in your water can affect it, and it can affect the taste, how you can change your water, and like how even the paper filters, how you pour from the kettle can affect it. Because the turbulence of water, depending on how you pour the water, can really affect it. And this is one thing that's super interesting. The only place I have ever found where scientific papers worried about a stream of water falling into a pool of water and how that affects turbulence. It's these chemical reactors that try to mix a gas with a liquid. So there's a lot of science there, but nowhere else, and it applies to like pour over coffee when you pour your. If you want to add more or less turbulence when you pour, it was all in these papers. So after looking for a while and really trying to understand every aspect, I ended up putting this together in a book because it makes sense. I don't know.
And your book's available in multiple languages, right?
Yeah, now it's translated.
That's fantastic.
Sounds like it's.
What's the title?
Deserves an Ig Nobel.
It's the physics of filter coffee. Yeah.
So we might have to have another Townsend talk just about that. Let's thank Dr. Gagné one more time.
On behalf of the Montreal Center, we thank you.
Yeah, thanks.
Now, you're talking about coffee. You hit something.
I see what's in there.
I roast my own coffee beans.
Oh, awesome. Nice.
And we could talk a lot about coffee. I don't know if you ever know James Hoffman on the internet.
Yeah, I do.
He's a coffee guru,
Yeah.
world winning on barista champion,
Yeah.
and he talks about the science of coffee at one level.
Yeah.
He measures his water
Yeah.
to the
Yeah.
ground. I mean,
He's a very nice guy.
very interesting, entertaining. So we know what's going to fuel astronomy is coffee.
Thank you so much. Oh, nice. Thank you. Thanks.
Okay, thank you very much. And back to talk about-
I'll take all the coffee questions now.
So we do invite everyone to come and ask more questions to
And-
Dr. Gagné. There's
Yeah.
still treats here, and
Yeah.
there's even some food left in the reception.
Yeah, and one other thing, got some handouts. If you like what you heard and want to help us and bring more talks, please throw something in here.
And more coffee.
More coffee.
Thank you, everyone. And it's a beautiful night out. We might set up some telescopes on the oval once everything's done in here. And so you're welcome to join us out there as well. Thank you, everyone.
I know people that bring, there's one, it's not here, but he brings a manual.